Hello everyone, I'm Wang Ziqing, the first author of AMD-DBSCAN. It's my honor to present our paper. My presentation is divided into 5 parts. First, our motivation. DBSCAN has been widely used in density-based clustering algorithms. However, traditional DBSCAN has 2 drawbacks. First, DBSCAN clustering relies on 2 parameters, which is EPS and mean point. For a point, EPS is the radius of the circle whose center is that point. All the points in that circle could be considered as neighbors of that point. Mean point is a first threshold value that can be utilized to search core points during the process of DBSCAN clustering. However, in most cases, it's hard to determine these 2 parameters, and it would take a lot of time and effort to modify the parameter artificially. Second, with the increasing demand for multi-density clustering, traditional DBSCAN that use only a 6-parameter pair could not give good clustering results on multi-density datasets, where different regions have various density. So what is multi-density dataset? Look at this photo. The photo in the left is multi-density dataset. We can see different clusters have different density, and in the right, the single density dataset has all the same density. So in order to address these 2 problems, an adaptive multi-density DBSCAN algorithm, which is also called AMD-DBSCAN, is proposed in our paper. And our contributions of papers are summarized as follows. An improved parameter adaptation method is proposed to locate the adaptive K based on the distributions of datasets, and we use binary search algorithms to speed up this adaptive process. Second, a new method for utilizing the K-distance value is proposed to search for multiple candidate EPS. First, an adaptive multi-density clustering algorithm is proposed to provide suitable parameter pairs, which is EPS and mean point, for each density cluster. Next, I would like to introduce our model in detail. And this is our framework proposed in the paper. You can see that AMD-DBSCAN is divided into 3 steps. The first step is parameter adaptation of K. The step 2 is to obtain candidate EPS list. The step 3 is multi-density DBSCAN. And first, step 1 is parameter adaptation of K. To achieve multi-density clustering on the datasets of extremely variable density, it is first necessary to obtain K required to determine the K-distance value. And in our paper, K means the K-paired neighbors of a point. We propose an improved parameter adaptation method to allocate these K. The distribution property of the dataset are utilized to generate a list of candidate EPS and mean point parameters. The EPS and mean point parameter lists are sequentially input into DBSCAN to obtain the number of clusters. After that, by using the binary search algorithm, we select the EPS and mean point pair that are the most match the distributions of the dataset for clustering, where mean point is used as K required for the next step. Second is to obtain candidate EPS list. The KDS value is defined as K-paired neighbors of a point, and the K-distance frequency histogram is a series of k-distant values arranged in ascending order, and the k-means algorithm is utilized to cluster the k-distant values to obtain n candidates here, where n refers to the number of peaks by directly observing the k-distant frequency histogram. First is the multi-density cluster. The first step is to solve the obtained candidate EPS list in ascending order, and each EPS can generate a corresponding mean point. Then data EPS mean points are input into DBSCAN for clustering. After that, the data that has been classed is saved and is not classed in the next loop. Repeat the above step until all the EPS are input into the model and the remaining data is the noise. The whole clustering is finished. Then is the evaluation part. In order to measure the difference in density between different clusters in a dataset, we propose a new metric, the variance of number of neighbors, which is called VNN. The value of VNN is a metric that reflects the difference in density of the dataset, which means the larger the value of VNN, the greater the density difference of the dataset. In this paper, datasets with VN less than 10 are considered as single density datasets, while datasets with VN greater than 10 are considered as multi-density datasets. Especially datasets with VN greater than 100 are considered as extreme multi-density datasets. Several datasets are selected for our experiments from UCI library, and because the multi-density datasets are of extremely variable density are hard to obtain, some datasets are generated to better test the performance of our algorithms. The make block 1 to make block 8 datasets are generated by sklearn2. To compare the performance on single density datasets, which is datasets with VN less than 10, for our proposed AMD-DBSCAN algorithm, some single density X-cluster approach, which is ROCA and PDD-scan are selected. The experimental result is shown in the figure. The number in the lower left corner represents the accuracy of clustering. As shown in the bar chart, compared to other two algorithms, AMD-DBSCAN has an average accuracy of 1.6% higher and achieved the best performance on the compound and plane datasets. In order to evaluate the performance on extreme multi-density datasets, which is datasets with VN larger than 100, for our proposed AMD-DBSCAN, some classical multi-density clustering approach, which is Yarding and AE-DBSCAN are selected for comparison experiments. The experimental result is shown in the figure. As shown in the bar chart, AMD-DBSCAN has higher accuracy on multi-density datasets than the other two methods. Experimental results show that our AMD-DBSCAN has the best performance on the majority of datasets. In order to verify the rationality of each step of AMD-DBSCAN, 3 sets of population studies are designed. First, test 1 and test 2 is to verify that the adaptive case from parameter adaptation process is valid. The selection of K is a great influence on the experimental results, which means when K is small, such as 4 in test 1, or large, such as half of the number of samples in test 2, the clustering results are very poor. This shows that the clustering effect of our adaptive case is better than that of the manually selected case. Test 3 is to verify that the candidate EPS obtained by the K-means algorithm is valid. Experimental results show that the clustering accuracy of our algorithms is on the average 8.3% better compared to the previous algorithm without using the K-means algorithm. In summary, the ablation study shows that each step of AMD-DBSCAN is necessary because it guides the selection of better parameter pair, thus improving clustering effect. In this paper, we present an adaptive multi-density DBSCAN algorithm which is called AMD-DBSCAN with high robustness and efficiency. The experimental results show that the clustering accuracy of AMD-DBSCAN is 24.7% higher than other algorithms on average for multi-density datasets and is 1.6% higher on average on single-density datasets. That's all. Thank you for watching.